So, hello everyone. It's our last day of our Female Clinician Engineer webinar series. Today is 25th of July and we are in the fourth day of our international female engineers that are presenting their success stories. So first of all, we have some ground rules. Wait, sorry for the technical. We have some ground rules and information. Our sessions are being recorded, so please do not turn on your cameras or microphones without being asked. For any questions, please use the chat and please stay with us until the end for our group picture. But most of all, just enjoy, learn, and have fun with us. So for today, we have the welcome notes that I'm now giving you. Then we have our first speaker, Parastoo Hashemi, who is a principal investigator that will present some analytical engineering. And then we have our amazing surprise Keynote lecturers. So now we can start with our first speaker. My colleague Banu will present her.
Hi, I am Banu, a researcher on cardiovascular engineering in Istanbul Medipol University. I'll be host of this webinar with Liana today. Our first speaker is Parastoo Hashemi. Hope I pronounce your name true. I'm not sure. Dr. Hashemi is a principal investigator of the Hashemi Lab Analytical Engineering. Parastoo received her Master of Science degree in Chemistry from King's College London. She performed her PhD with Martin Bottle in the Department of Bioengineering in Imperial College. She developed online biosensoring technology to measure brain metabolites from human traumatic brain injury patients. After her PhD, she skipped over the pond to Chapel Hill, where she worked with Mark Whiteman. Here she learned fast second cycling voltammetry, called as FSCV, at carbon fiber microelectrodes, and developed the first method to measure serotonin in vivo using FSCV. She has held a variety of academic positions in the States and in the UK. Parastoo and her team tackle some of the world's most pertinent issues with analytical engineering and have a long list of accolades attesting to their success. Now, Parastoo will present her presentation, and we are very excited to listen to her. Welcome.
Thank you. Okay, so I'm going to share my screen. Everyone can hear me?
Yeah.
Could somebody possibly drop me a text a chat when I have maybe like 3 minutes left?
Mm-hmm.
So I can start wrapping up. Okay, so I'll start now. Let's see. Okay, here we go. So thank you for the invitation to speak. I'm going to share a piece of one of the big stories that we've been working on in my lab. It's a very long story, so I hope that I can take this piece and make sense of it. You know, we're an engineering lab, but we really have strong interest in understanding the brain, and our real sort of biggest interest for the last decade, I'd say, is oops, where are we? Sorry, we go right to the start. Our biggest interest has been depression. So I'm going to start off the talk with this quote from American psychologist Martha Manning. Depression is such a cruel punishment. There are no fevers, no rashes, no blood tests to send people scurrying in concern, just the slow erosion of the self, as insidious as any cancer. And like cancer, it is essentially a solitary experience, a room in hell with only your name on the door. I'm sorry, that's a bit morbid, but I like this. I like this quote because I think that it actually speaks to a lot of the issues that we're trying to tackle with analytical engineering. Depression is a significant public health issue. 300 million people in the world are diagnosed with depression. As probably only a fraction of people that actually suffer because of the stigma and the taboo that goes hand in hand with mental illnesses. Just to put that number in perspective for you, 100 million people suffer from cancer of any type. So this is clearly a huge problem. It's very difficult to diagnose. If you suspect you have depression, and you go to a doctor who's willing to listen, it's really sort of their opinion based on some questions that they ask you. So there's no, test for this, if you like, at least like a blood test. Despite this, it's very difficult to diagnose. A huge amount of people are prescribed antidepressants. The numbers sort of vary, but the last time I searched, it was something like 1 in 12 Americans. It's a massive number of people. The most popular of these antidepressants are the SSRIs, and they don't work well for the vast majority of patients who take them. For about 70% of patients, they don't have clinical relief. And if you've ever taken them or know anyone that's taken them, there's problems with dosage. You often have to go back to the doctor quite a few times to get the dosage corrected. They have this curious thing where they take several weeks to take effect. And all of these problems sort of combined has actually made Big Pharma lose interest in. About 10 years ago, Big Pharma sort of dramatically toned down their drug discovery efforts for new SSRIs and new antidepressants, because frankly, they have no ways to screen the potential efficacy of lead compounds. Okay. So we've got a problem, we've got quite a few problems, and the question is why? Why do we know so little about these things? And the answer is that we don't have, at least until not recently, we haven't had really very effective ways to probe the brain. So this is the sort of overriding theory of depression. It's called the monoamine theory of depression, and it was developed in the 70s, and it's sort of come in and out of fashion over the decades, but this is sort of how it goes. And this theory precipitated the development of the SSRIs. So here you have a presynaptic cell, and here I have a postsynaptic cell. This is an example of two neurons communicating in the brain, and this is sort of the basis of the essential mechanism of brain function, if you like. So here's two neurons communicating through what is known as a gap called a synapse. The presynaptic cell will release a neurotransmitter. Serotonin is a good example that's really implicated in depression, and it has an effect on the postsynaptic cell, and it's basically a biochemical message that's relayed and does the communication between two brain cells. Okay. The theory goes that in depression, for some reason, the serotonin that's in this space is lower in concentration, and that by inhibiting a protein on the presynaptic cell that's tasked with taking the serotonin back into the cell after transmission, you can increase the serotonin levels and relieve the symptoms of depression. It's only been a theory because we haven't had a way to really capture these processes. Measuring things in the brain is very, very difficult. So as you can imagine, as a theory, it's difficult to sort of refine it if you don't even know whether it exists or not. So this is sort of where we started. We said, if we want to tackle depression and think about destigmatizing depression diagnoses, and then if we can do that, maybe we can make better measurements and sort of really contribute to this field, we need to look at three different things. We need to think about how to make a diagnosis. To make a diagnosis, you need to have something that you can test, a hypothesis, like that monoamine hypothesis of depression. You need to be able to measure something chemically to then be able to sort of say, yes, the hypothesis holds or no. And the majority of work that's done on, psychiatric compounds are done in animals. So how translatable is that to humans? Second thing we want to think about is depression treatment. And we want to tackle that sort of variability. By that, I mean the fact that the antidepressants don't work for 70% of patients who take them, and then a time frame issue, where people have to take them for 3 or 4 weeks before they see an effect. And again, is that translatable? Finally, we want to be able to look at sort of, can we engineer methods that would actually give accurate screen of potential compounds and make those also translatable and personalized. So I'm going to talk to you today primarily about this first part and a little bit on the second part, but we've done significant work in all of these three aspects, and if anyone's interested, I'd love to have that conversation with them after this talk. All right, so let's jump into the diagnosis. I mentioned that it's very difficult to measure things in the brain. It's not like you can take a blood sample and it'd be informative. You can't really take a brain sample for one. I mean, it's not possible. But even if you did, it wouldn't really be informative because, like I said, those two neurons that are communicating, this is a very rapid dynamic process. Within the sub-seconds, it changes from one thing to another. So sort of taking a stationary sample wouldn't give you much information. You want to capture what's happening in the brain as it's happening in real time. So the technique that we use is a real niche technique. It's used really by a handful of people around the world, and we've pioneered this method for serotonin, so very few other people can use it for serotonin. We make electrodes. They're made out of carbon fiber, so this is a representation of an electrode, and they're very, very tiny. They're 5 microns in diameter. You can implant them straight into brain tissue. I'm going to talk about work that we've done in mice. The electrode is so small that it doesn't create any sort of tangible tissue damage that would actually interfere with the neurotransmission processes. And then I'm going to talk to you a little bit about the technical aspects of the measurement. But in short, we can make 2 types of measurements. We can make a measurement of that sort of steady state ambient resting level of serotonin that I talked about that was between the cells. So this is going to be represented by these red balls here. I'm going to call that ambient slow chemistry. With a technique called FSCAV. We can also induce cells to release serotonin rather quickly, so they can release a burst of serotonin, and we can measure that with a technique called FSCV, and there we'll see how serotonin is released and reuptaken by the cells around it within the order of seconds, basically. So we're going to look at fast chemistry and slow chemistry, okay? I'll go relatively fast through the technical aspects of it because I really want to get to the meat of the exciting stuff. So bear with me while I go rather fast here. The base technique that we use is electrochemistry. So here's the electrode, it's implanted into the brain tissue. Serotonin as a molecule here has electroactivity. It means that a certain energy we can gain, and we can take and we can give electrons to the serotonin molecule. So what I'm showing here is a 2-electron oxidation reduction of the serotonin molecule at a certain energy. In this case, it's a potential energy. So this is a potential waveform that's applied to this electrode at a certain energy. You can capture the oxidation process, which is the loss of electrons. At a certain energy, you can capture the reduction process, which is the gain of electrons, and you get this signature cyclic voltammogram here that basically, all you need to know about this is that it identifies the thing that we're looking at, and the height of this peak, the current of this peak, tells us how much of it we're looking at. So we can, by using this technique, very rapidly, once every 10 milliseconds, get a signal where we can identify as serotonin, and we can quantify as serotonin. This is the in vivo model that I'm going to share with you in mice. So this is a sagittal slice of the mouse brain. His eyes would be here, his tail would be here, and we put the electrode in an area called the hippocampus. It's an area that's important for depression research. We can also put it in other areas. This is an area called the hypothalamus. And we make 2 types of measurements. First, we just drop it in there and take a measurement every minute of that steady state ambient level. Otherwise, we stimulate an axonal bundle that comes out from a cell body region that makes serotonin. If we stimulate that electrically, we can get that faster response that I talked about. This is what that fast response looks like. So we start here, and we stimulate right here, and then you get the serotonin going up during the stimulation. After the stimulation, it's cleared. And the sort of beauty of this sort of signal is that this portion of the curve tells us about how that serotonin transporter, remember the agent that was blocked by the SSRI, the protein that was blocked by the SSRI. This is the kinetics of that protein. And this is basically a model that we use to model this curve. And this talks about the kinetics of the reuptake proteins that take serotonin back up. And what I'm showing here is data in male and female mice. And basically you can see that this is sort of unnormalized data that the male and the female mice have pretty much exactly the same type of fast serotonin signaling. The second type of measurement is that FSCAV. We developed it in my lab. This is to give you the slow minute-to-minute measurement. Again, I'll go real quick through this. Basically, what we do is just a sort of a variation on the FSCV method. We apply the waveform to the electrode very, very fast to begin with. This minimizes what can happen to the electrode surface. So it's essentially a clean electrode surface. Then we turn the waveform off for 10-15 seconds, and we allow the serotonin to come and sort of reach a steady state on the electrode surface. And then if we turn the waveform back on, we can oxidize and reduce everything on the electrode surface and compare it to the blank. So basically within that 10 or 15 second period, we can know what the ambient or steady state levels of serotonin were. And again, we can quantify it with CV. There's an in vivo CV and an in vitro CV. They show pretty good agreement. And here the data is going to be a single point with time. So whereas before we had a this sort of topography of release and reuptake. Here we're going to have 1 point, a minute later we're going to have another point, a minute later we're going to have another point. Okay, so I've just whizzed through pretty much 10 years of development research for you, but I want to get to the exciting stuff. So we developed these methods. Took a long time, but what we wanted to know in mice is whether this monoamine hypothesis holds, basically. So is serotonin actually lower in mice that have depression phenotypes? And so what I'm showing you here is data from a cohort of mice that have been have undergone a chronic stress paradigm. So there's a bit of a long story about how we do that and how we ascertain that the mice are depressed, but these mice have depression phenotypes, and if we measure the serotonin, that ambient steady state serotonin in their hippocampus, and compare it to mice that don't have depression phenotypes, you can clearly see that actually the serotonin levels are lower in the mice that had the depression phenotype. So that's, I mean, I suppose not exactly surprising, but a little bit surprising, because we were sort of expecting to see something different given the variability of the SSRIs and the problems with how they work. But anyways, we saw this, and this is very robust. We have many different models of depression, and we see this sort of lowered serotonin. Okay, so this is exciting because now we sort of have, you know, a quantifiable biomarker. Yes, there's problems with measuring things in the human brain, and we can talk about that. We have ideas about circumventing that, but at least in mice, we can make a measurement, and that correlates very nicely to the mouse's depression phenotype. So let's jump into the idea of treatment. So, you know, like I said, the SSRIs are not particularly, do I have 3 minutes? Is that what you're telling me? No, okay. So, oops, sorry. So in terms of, like I said, the SSRIs are not particularly efficacious. They work for only 30% of patients who take them. And if you know your pharmacology, that's right around placebo range. So not working very well. So we want to know why. Now, if you've been sort of following any sort of pop health literature, you will have seen the word inflammation in the past 5 years. Inflammation is very hot right now. Everyone's talking about how inflammation is linked to different types of diseases. But one thing is very, very clear, that there is no depression without neuroinflammation, and there is no, neuroinflammation without depression. These two are extremely, extremely comorbid. So what is neuroinflammation? Neuroinflammation basically is a blanket term for your brain's immune reaction to something. So it could have many different causes: trauma, infection, toxin ingestion, various different things. It sets off a cascade of biochemicals. This is quite a complicated slide. We don't need to go through it, but it sets off a cascade of very complicated biochemical events that create inflammation, a immune reaction in your brain, but then, like I said, a comorbid with psychiatric disorders. So we did an experiment that I thought was pretty neat. Let me talk you through this. So now we're looking at this minute-to-minute measurement, okay? Here we measure serotonin in the blue in a cohort of mice. At this point, we give the mice saline, nothing much happens, you wouldn't expect it to. And then at this point here, we give the mice an SSRI, escitalopram, and within a few minutes, the serotonin levels start to go up. In a separate cohort of mice, after 30 minutes, we give something called LPS. LPS is a protein found in the outer membrane of gram-negative bacteria, and it causes a very large acute inflammation reaction within the body. But as a molecule, it's too big to actually get into the brain itself. But look at this. Precisely 5 minutes after we give the LPS, the brain serotonin levels start to decrease. So the brain serotonin levels are decreasing in response to the LPS. When we give these guys now an SSRI, you can see that the serotonin increase is neither as large nor has a slope, anything like the control guys. This is the case in our guy who had depression phenotypes that has been chronically stressed. They also have a chronic inflammation. And you can see that when we give these guys SSRI, the serotonin levels don't go up as high nor as much. And if we merge actually the acute and the chronic models, there's pretty good agreement. Really, it's quite stunning that the serotonin levels go down the same amount in response to the inflammation. Okay, so what do we think this is? I'm going to just jump straight to the punchline because we don't have time to skirt around the issue. We think it's histamine. Here's why. We know a lot about how histamine modulates the body's immune responses. So that's pretty clear. We take antihistamines when we have allergic reactions. Much less is known about how histamine modulates the brain's immune responses, but we do know that there's histamine in the brain. And it comes from mast cells, it comes from glials, but it's also a neurotransmitter in the brain. So we created a technique to be able to measure histamine in the brain with the same electrodes, and we found something really cool. And this is backing up stuff that people had previously found. So we measure histamine and we measure serotonin simultaneously. The histamine is in blue, the serotonin is in pink. If we go to a region where both are present and we evoke histamine release, we actually see that it's followed by a profound reduction in the serotonin release. So histamine release is inhibiting serotonin release. And this is sort of signified by this diagram here, where there are inhibitory H3 receptors on serotonin neurons. So when histamine is released, serotonin is inhibited. Here's what we did. We took a couple of different models that we had in our lab that were inflammation. So one is chronic inflammation, one's acute inflammation. And since then, we've managed to actually add a spectrum of different things to it. And what I'm showing you here is that serotonin and histamine dual response. So histamine in this guy, the control is blue. When this guy has inflammation, you can see there's more histamine. And there's more inhibition of serotonin. And when we gave that LPS, you know, that acute inflammation I showed you, again, we have more histamine, and as a consequence, we have less serotonin. So we think that extra histamine in the brain during neuroinflammation is driving the serotonin down. So the final experiment we did, this is my final data slide, to sort of hammer that home, is an add-on to the experiment that I already showed you. So here we have serotonin measurements for 30 minutes. We give saline, nothing happens. We give the SSRI and the serotonin levels start to go up. Remember when these guys got LPS, the acute inflammation, the serotonin levels went down. So now we have an extra cohort that we did that with, the orange guys, their serotonin levels go down. But at this point, whereas the gray guys that you've already seen only got escitalopram, the orange guys got escitalopram and an agent that targets the production of histamine in the brain. So basically reduces the production of histamine in the brain. And you can see when we give these things together, the serotonin levels can go back up to the control animals. And it's precisely the case in our guys that had chronic mast stress. So they have chronic inflammation. If, in addition to the SSRI here, we give them an agent that targets histamine synthesis, we can get the serotonin levels to go back up to control. So we're really excited about this as a potential new treatment strategy, and a way, if we can measure the serotonin and the histamine robustly in humans, as a way to actually be able to diagnose depression via neuroinflammation. Okay, so that's all I wanted to say. Basically, I've talked to you about this idea of coming up with a testable hypothesis and being able to measure it chemically. Right now it's in mice, but like I said, we'll have a whole program now to be able to translate this into humans. That's a whole other talk that I could give another time. We've looked at, the tick is in the wrong place here. We've looked at the variability of the issue. We think it's due to neuroinflammation, but we also think we figured out the time frame issue. That's again a whole other talk. And again, translating it to humans. And then finally, we have plans for figuring out how to take that biomarker and novel treatment strategy to think about screening for new compounds. So I'm going to stop there, and I'll just stay on the slide that other people, all of these people did the work, a ton of them. I won't really mention them because there's so many of them, and the people that funded the work also. So thank you again for letting me speak. I hope I didn't go over too much, and that's it.
That was a great speech, Dr. Perry. It was very amazing and mind-opening because it's related with many fields, just biophysics, biochemistry, computational methods, and neuroscience, lots of things. So it was very complex, but you explained very well, so we could understand somehow, because it's not easy to understand. Very different multidisciplinary stuff. So thank you very much for this nice presentation. It was very motivating for me as well. And we have questions. Liana asks, which models of depression do you have and use in your lab?
We've tried many of them.
Mm-hmm.
So there's, you know, there's quite a few. There's the behavioral models, and so, you know, we prefer the mild stress, but there's also more rapid ones. So there are the ones, there's the defeat stress. I don't know if these things mean anything to you, but there's defeat stress. There's also, there's genetic models that you can get. There's also neurodegeneration models. There are models of toxin ingestion, so lead, for example, ingestion will do it. So there's actually quite a lot of things. And this is something we're interested in because we want to know, we know anecdotally that these things create depression phenotypes in animals, but we actually want to know, now that we sort of think we have a biomarker, we want to know more precisely the etiology of depression, so that this is another thing that I think is really important for clinical practice, is not just diagnosing and treating, it's actually saying these are the things that you can do to prevent. There are, another thing I didn't mention that's so important now, there are pretty robust gut models of depression. So you can take animals that have poor stomach bacteria that have depression phenotypes. So yeah, there's quite a few of them. And we've used 5 or 6 different ones, but we want to use more.
And it is a very productive lab with innovative biosensors devices. So, what is the next step for your future plans? What is the next step of your study, or maybe converting these methods to another field, maybe another neuroscience problem?
Yeah. So the thing that we're doing quite a few things, but I'll tell you the thing I'm really excited about. So the story that I've told you is that we've been working on, and we've sort of finished it and polished it. My desire now is to translate it into humans. We're looking at a variety of different ways to do it. It's not easy, but the thing that we've been working on that's wildly exciting to me is human-derived stem cell cerebral organoids. So basically, you can take cells from us, and they have the information in the DNA to be able to basically be differentiated into a mini hippocampus, right?
Yeah.
And so we're doing this. We're working with some collaborators on making these organoids. And then the question is, can this be the translational model that we're looking for? And that's wildly exciting, because and you really sort of can imagine that we would have a way with our techniques and that technology to make a measurement and make that diagnosis. And not just that, to figure out exactly what is the best treatment strategy.
Yeah, it's amazing. And this is really a real public health problem. So you are working on at diagnosis and treatment side, both those sides. That's very amazing. Liana says it's very exciting talk, a very important topic. Thanks. Also, she has another question. Have you also checked the hypothesis in vitro models?
You mean like cell slice preparations and stuff like that? Yes. Yes, sort of. I mean, we once we got in vivo, we were just so excited. But you're absolutely right. We need to sort of step back and look at it in some of the more simple models. And yes, we've looked at. You're absolutely right. A hippocampus. It's a hard one, because if you've done this sort of research, to get a data set, it's like 4 or 5 years of work. So we stuck to the hippocampus because that's where we started. Now we can make the measurements in different places. We've looked a little bit in the prefrontal cortex and a bit in the amygdala. We need to do it. I agree. It's going to take several years, to actually come up with an answer for you. But yes.
Yeah. Thank you. You answered the other question as well. So, and I wonder, what is the process that brought you to this beautiful work field? So there are lots of branches of your study, your research field. What made you to work on this stuff?
It's a very good question. I was we're sort of interested in the brain, various aspects of it, and I'm sort of I started off as a chemist and an engineer. And when it sort of became time to decide what I wanted to do, I really decided I wanted to work on psychiatric illnesses because, to be honest, I have a really close family connection with psychiatric illnesses. And it's something that is, personal to me and important to me. So I started doing it. But I'll tell you something else. So since I do this work, everybody I talk to will share with me their own experiences with psychiatric illness. So I've come to realize over the years actually that it's part of, you know, the human condition. We all suffer in some respect. We all know someone who suffers. It's just that people don't generally talk about it. And so for a long time, I thought this was such a sort of a personal, special deal for me, but I actually realized that it's important for everybody. And I'm just really happy to be able to sort of look at something that's that important to me.
You are doing great. It's very amazing. Thank you very much, Perry, for this mind-opening talk.
Thank you so much for inviting me.
Yeah, it was very nice. I'm sure that the audience enjoyed this very much, and you motivated lots of people, I think. And also, the record will be watched in YouTube, so maybe our students also will learn much from this presentation. Thank you very much.
Thank you so much. Thank you.
And now Liana will announce our keynote speakers.
Thank you, Banu. Thank you, Perry, for your presentation. It was actually great, especially for me that I'm actually working in the same field, so thank you very much. So now the moment of truth. We have our amazing keynote lecturers. We have two keynote lecturers today. We have Clare Morden and Cristiana Pace, who are from Formula One and will present about their path as engineers, as clinicians, and please welcome on stage. Thank you very much for joining us today.
Thank you very much for having us today.
Thank you.
I will just share my screen. So you should have this up, and so my name is Clare Morden. I'm actually not an engineer, I'm a doctor by background, a clinician. I have been involved in motorsport for many years and was lucky enough to meet Cristiana through the work I do within motorsport. So I'm a doctor in tracks in the UK, but specifically at Brands Hatch, and I also work on Formula One and Formula E, which is the sort of area where Cristiana works more. We, as you can see on our lecture, are both ambassadors for Dare to Be Different. Dare to Be Different was started by Susie Wolf a few years ago, and the idea was to get females involved in motorsport. Unfortunately, it's still one of the areas, like engineering and quite a few science areas, where women are not necessarily coming through, and certainly in positions of power, women are few and far between. So the idea was, when Susie Wolf retired from driving, she made it as a test driver in Formula One, that she would set this up, and there was an education element to it as well as a networking element. So the education element went into schools, and we had girls coming to the events learning about engineering, medicine, journalism, presenting, and they even did some driving as well, showing that motorsport isn't just about the drivers, as some of them would have you believe, but it's a big support network as well, with a lot of other career options involved in it. The other side to Dare to Be Different is the networking side. So you could become a member, and within the network, there were meetups and educational events where you'd have speakers and opportunity to meet other people. Within it, I have become very friendly, obviously, with Cristiana, but also with a couple of photographers who were just starting out and then went on to win amazing prizes with their photography. But also it's get open doors for us to work more closely together when maybe we didn't even realize we necessarily existed before that point, okay? Dare to Be Different has undergone a transformation this year. So if you are going to look for it online, have a look for Girls on Track UK. It has been blended into the FIA, which is the Federation International Automobile, which sort of oversees it all. So I'm going to now hand over to Cristiana in a moment. Can I move my slide over? There we go. So I've covered the short introduction, which I will go to in a moment. Cristiana is going to chat through her biography. Also, Cristiana is an engineer by background. So she's going to talk about how she's been involved in improving safety and the collaboration between us. And then I'm going to chat through my biography, what it means to be a chief medical officer, and why the connection between engineering and medicine is so important. So now I'm going to hand you over to Cristiana, who is in the depths of the English countryside and has a very poor internet connection. So you won't see her, but I do believe you are going to hear her, I hope. Cristiana?
Can you hear me? So, okay, so hello, I'm Cristiana Pace. I'm originally from Italy, and as Claire said, I'm an engineer by background. This is a quick run through what I've done in my life that is mainly motorsport. So I graduated at Bologna University as industrial engineers, and I did my thesis in a company in England that was already doing motorsport. And just before graduating, I became like a scrutineer from the Italian Federation of Motorsport, and that's how everything started. So I got involved in as a race engineering for GT, as a strategy engineers for the 24 Hour of Le Mans, and then I went to Cranfield University to do my master. And that is, I did a master in motorsport, and that is where I actually thought, I could really work in motorsport. I really like this industry. I really want to be part of it. And then when I finished my master, I started to work with M Motorsport. That was a spin-off of Magneti Marelli, that is an electronic company, and in the FIA Formula One technical department. And I worked for them quite a long time, and my task was mainly acquiring data from devices that I had in the car. Initially, it was for checking if anybody was cheating, but as things evolved, it was to develop new systems to improve safety in motorsport, and also to reconstruct the accident and see what could be improved in and off the track. So because of this work that I was doing with FIA, I also became part of the FIA Institute for Sustainability and Motorsport Safety, where I met Sid Watkins. That is a common denominator with Claire, actually. We all got inspired by this fantastic doctor that was trying to build safety in motorsport, but also use motorsport as a way to collect the data to understand a bit better about other medical problems that could be sorted. And then after my times in F1, I decided to join Williams Advanced Engineering. At that time, I just decided that I didn't want to travel that much, and the F1 traveling to every race is very demanding, and sometimes is not the best way to have a family and start a family. So at that point, I decided to move from traveling to every race and every test of F1 to Williams Advanced Engineering factory base. That was actually a spin-off of Williams F1, and it was transferring technology from motorsport to other departments, including medical. And I left Williams in 2015 after being in charge of the Formula E project, the electric cars. Williams did the battery for them, and I started a PhD. And the PhD was on sustainability and strategy management, but was actually investigated the ecosystem of Formula E, so was still motorsport and the transition to sustainability. And just in the last year of my PhD, I founded my company, Innovation Consulting. That is a company that has got the aim of trying to help with engineering for other sector rather than motorsport, and with sustainability for the motorsport sector, because obviously motorsport is not yet that sustainable, but would be soon, and also trying to help with education. Claire, if you can move on the other slide, sorry. Yeah, that is a bit of summary of what my company does at the moment. So like a speaking engagement. So we got the Dare to Be Different Girl on Track project, for which I've done the STEM, the engineering's activity, and I deployed that with them all over. But also I'm doing quite a lot of still with engineering and with cars. Claire, if you can move on. So these are more or less most of the devices that I've implemented in my time in the FIA. Some of the devices didn't exist at all, and they actually were invented to fulfill the lack of way to acquire data to study the accident. So I started with the surveillance data recorder that is acquire all the data from the car so you can do the accident reconstruction, and then we actually migrate. For example, if you see there are some ear plugs there, and they have got a small accelerometer in 3 axes so that you can actually acquire the movement of the head of the driver when they have got an accident, so you can actually also see what's happening with the speed of his head and simulate his brain as well. But also we invented with FIA the marshalling system, that is a way to give flag electronically at the track so that we can keep the marshal a bit more safer. If you can move to the next slide, please. So one of the things that was really important for us at my time at the FIA is this idea of collecting data. And that was something that we started in 2004 with the IDR program. So we wanted to collect data to do some investigation on crashes and then research into mitigation and what we could improve to make the driver safe. So if you see on the top right-hand side of the slide, you got a big crash in 2007 with Kubica, where he only injured his foot, thanks God, but it was a very, very massive crash. And we collect all the data from that accident through one of the boxes that I showed before. And with those data, we created a graph that you can see on the bottom left. And that graph gives you peak G and velocity and deceleration and all that parameters that can help you to understand as well how the body, well, can feel two objectives. One is to help you to understand how the car has crashed and what can be improved in the car. But the other things, it can actually help you to understand what the body of the driver was. So what normally the FIA does after reconstructing the accident, they actually simulate the accident on this ledge and trying to improve new safety standard and put the regulation and suggest regulation to put in place to improve safety. So this is what we were trying to do. So from acquiring data to trying to find a way to improve safety in motorsport, but also improve safety of the driver itself, and trying to study what was the human reaction to the impact as well. If you can move over, please, Claire. So this is something a bit different, but at the same time still coming from the motorsport. So when I moved from the FIA to Williams Advanced Engineering, I was tasked to actually write a strategy for Williams Advanced Engineering to transfer technology to other sectors. And we did transfer to many other sectors, but one of the things that we really wanted to do is to transfer some knowledge to the medical sector. So on the left top, you can see a picture with a pod, with a baby. That is something that we developed with the Williams Advanced Engineering and the NHS, and it's called Baby Pod. So we actually put together the idea of suspension and the idea of an environment where the baby was kind of not prone to infection, to transport a really premature baby into ambulance, because the problem there was the vibration of the ambulance and the transportation inside the normal incubator. So that's how we transfer what we knew from Formula One, all our knowledge from Formula One and motorsport, we transfer it into this device. And that was the first, I think it was one of the first technology transfer into medical. And then we had many others, like for example, we had McLaren with data through the NHS. They monitor remotely some patients that have got diabetes. Then you can see on the, well, obviously with COVID, we had many more. So you can see on the right top, there is like actually is is something that Ferrari has created for the Italian equivalent of the NHS, and is a respirator, and is a small simple respirator that can be used in ambulance as well. But then you got on the bottom side, you got something that the UK Formula One and motorsport teams have tried to transfer into the NHS as a response to COVID. So you got a valve that Mercedes has developed for the respirators in the UK. In the middle picture, you've got actually the gown that were, there was a scarcity of gown during the COVID. So Aston Martin actually put the people together to do these gowns because they had the machine to cut pattern, so was kind of repurpose their composite material shop into making gown. And then on the last image on the right hand side is something that I was involved personally, that is called the Oxford box. That is an aerosol box to try to protect the practitioners and the anesthetists when they're intubating the patients. The peculiarity of this box is that we used CFT to try to simulate the particles and to actually study the viral load and when the particles settle, and for telling people when they could remove safely the box. So it's like when the viral load was lower than it would be normally is. Something that hasn't been done in the other box that has been in the market, and something for which we are now talking with Manchester University and with a retired doctor from the WHO organization to try actually to progress with this kind of study, as there is a lack of like use of this kind of methods like computational fluidodynamics for in the medical world that obviously the motorsport world can bridge, because we use computational fluidodynamics to create the car. So that's yeah, next one. And then I leave you to the fantastic Clare. It's like she's really great, and you will hear her story.
Thank you, Cristiana. So I'm just going to tell you a bit about my background, how I got involved in Formula One as a doctor. So there's a strong family interest in my household. So growing up, my mum, my brother and my dad would always watch it. My sister would never watch it and be alone eating her lunch. And I always wanted to get involved in motorsport, but certainly not as a driver, but I have always wanted to be a doctor as well. So up in the picture in your top right, you can see Ayrton Senna in his blue overalls talking to Professor Sib Watkins. Cristiana alluded to Sib Watkins earlier. So he was a professor of neurosurgery in London, but in the 70s and 80s, he had an interest in motorsport and went on and developed the motorsport medical centres that we're using today, essentially. And the idea was to deliver as good a hospital care in a pre-hospital environment at the side of the racetrack, which is what we try and achieve to this day, so that whether you crash somewhere remote, you still had all the medical facilities you would need to try and stabilise you before being transferred elsewhere. I've always wanted to do medicine, and certainly I was very fortunate because it was a conversation with a friend who is now a paediatric intensive care consultant that I said, oh, I really like my motor racing, and she said, come along. And she did it in her weekends, and I went along fresh from university. So I was in my first year out of university as a doctor. So my biography, I've got at the top, I've got what I would call my day job within the NHS in England. I am an intensive care doctor, so we have been quite busy at the moment with COVID. I'll be honest, it hasn't been much fun in the UK, as I know it hasn't been in several areas of the world. So we have been very busy. So I went to university actually in Prague. My mum's side of the family are originally from the Czech Republic. I grew up here, went and studied actually in Czech, and then graduated from there. Before I did that, as I'm sure all of you are aware, you have to do work experience, do all your activities to make you look interesting and things like that that go alongside it. I then was in Bristol, so medicine in the UK, you move around a bit to get experience at different hospitals. And when I was actually working in a place called Swindon, was when I had, at the bottom you'll see my motorsport career, the taster day as a doctor at Thruxton, which is a racetrack near to there. So then I did my foundation years, thought, what am I going to do with my life? Knew I wanted something exciting and interesting. So I thought, right, I'm going to do emergency medicine. And so I started doing my emergency medicine training, and which I know some countries don't have the same, some do. But essentially it's your first response and your emergency departments are where people first come to in the UK in hospital. Alongside that, I was working on my spare weekends, which are few and far between, but I was working them as a doctor at various tracks around the UK. So I also became an instructor in, for those of you with a medical background will know ALS, so that's Advanced Life Support and Advanced Trauma Life Support. From then on, I moved to where I live now, which is Wessex Deanery, down near Southampton. I'm actually based in Winchester, but I'm working at Southampton and Portsmouth at the moment. I have now specialised in intensive care solely, with the aim to become a consultant in that and pre-hospital care going forward. Alongside this, I carried on with the motorsport, plodding along, trying to get my foot in the door every step of the way. And then I was asked if I'd consider being the Chief Medical Officer at Brands Hatch, which is a very busy circuit in the south of England. I then was working at an event called Race of Champions, couldn't even think what it was then. Race of Champions, where I met Susie Wolf, who was setting up Dare to Be Different. So then I came on board, became an ambassador of that, did education, then acted CMO at Silverstone. I've now been fortunate enough to go to Formula E as the extrication doctor, which is very, very interesting because you're working along quite a multidisciplinary team to extract the driver. And I'm also chair of the European Resuscitation Council, the Young ERC. And I've set up a charity called Heartbeats UK, which you'll see at the bottom, which is about teaching resuscitation skills and CPR to young children, because many countries do have that in place in schools, but in the UK we don't yet. So that is something that hopefully will develop. I'm now, as you can see, progressing. I'm now on the medical committee for the Motorsport UK, and I've just been announced recently as Chief Medical Officer for electric touring cars, which was meant to start this year, but due to COVID has not. So I think it's a new series that will start next year, and it will be very, very exciting. It's a new way of racing electric cars. So my role, yes, I am medical, but at the racetrack, I have to do not just the medical part of my job. And that is actually very interesting and novel for me, because in the NHS, my day-to-day, particularly at the moment, has been a lot of COVID, ventilating, unwell, difficult conversations. I am in charge of the medical team, which can be very small. It can be 3 or 4 people, or it can be a bigger event. You see in the bottom right corner of us all in red overalls, that's the German touring cars. And then I might be part of a bigger team, which I will be next weekend and the weekend after at the British Grand Prix at the Formula One. So at the moment, I'm also in charge of doing driver medicals, the fit to race. Drivers can be as unwell as us, but we need to make sure that they're okay to get in a race car and have their heart rate go fairly high and have that stress put on their bodies for a prolonged period of time. So if they've had diarrhea and vomiting, for example, we need to make sure they're adequately rehydrated and they're going to be okay in that situation, because actually their overalls, fireproof overalls, they get very, very hot in that environment. I'm also involved in the management side, so the rota coordination, ordering drugs, ordering equipment, which I have to say in the NHS you just leave to someone else to do. That's quite novel. And training, which we have a big emphasis on now, and recruitment and development. So the development is very interesting, and it's something that I'm lucky enough to have met Cristiana and been involved with the engineering side, but also it's developing new people to come in and develop motorsport medicine as a sort of pathway that people will be interested in doing. So from the CMO role, it has made me think, why is it so imperative that we combine engineering and medicine? And these graphs, I think, demonstrate it very clearly. So the top one with the blue, red and green lines on show the driver deaths and per decade. So the 60s and 70s, bad decade, okay? And you can have a look here and you could see the number of Formula One deaths in years from the 60s. So you're having 14, 15, 16 drivers die a year on average, which if you look to now, it is very few and far between. So the red line, 2000 to 2008, no one died in a Formula car at a race meeting. So blue car is your NASCARs, which is over in America, and your karts, which are also in America, is your green line, okay? There is some variation, but generally downward trend. Now, what's interesting now is if you go to the other slide, you'll see the average speed as the decades have gone on. So that has increased. And the electronics has increased. You can see some interesting bits in the engineering there. You've got turbochargers, you've got high-tech electronics, which essentially drove the car for you to some extent, which some have been removed now, but some are still in place. And you've got the development of aerodynamics. Why is it important? Because we need to try and stop the death, which we can do a bit of, but not a lot. But the engineering side can do a lot of, okay? And that's where it becomes important, because although we can get to a driver, dependent on the type of impact, we may already be too late. But when you've built a car that is so safe and secure that you can be doing 180 kilometers an hour and walk away from that, that's where the interesting bits between engineering and medicine collide. So it's imperative, really. There's lots of areas that you can talk about through the decades where engineering has played such a vital role in motorsport safety. You can go back to the 50s when they were driving cars without seatbelts. And oddly enough, there are a lot more fatalities. Now we have these seatbelts that are rigorously tested. We have fireproof overalls, we have helmets. One thing recently that has come out, which is very interesting, is the HANS device. Some of you may be aware of it. It stands for head and neck support. And what it is you can see in the diagram there on a driver, it sits over the shoulders of a driver with a collar up at the back, okay, up behind your head. And there are two clips either side of your helmet that clip onto your helmet, okay? And this was developed to basically eliminate or try and reduce the risk of what we call basal skull fractures, which is when your head is rapidly, essentially you're accelerating, it's rapid deceleration, and your brain injury is so great and your skull is impacted, it's normally a side impact, causing a basal skull fracture. And that is actually what a lot of fatalities were caused by. So you can see that picture here. That's actually a picture of Dale Earnhardt, who was racing in America, and that was in 2001. And that is essentially what impact was that killed him. And there is some thought that if the HANS device had been in place, it would have minimized that movement because you are tethered to your shoulders, essentially. Okay, so that was very interesting. And you can see here, without a HANS device, the force going through your neck and the shearing forces, which is what causes those head injuries, are so great. And red, the red line, is where you get those injuries. So that's very interesting, the HANS device, and it's something you can look about more. but now all formulas of drivers are expected to wear them in the FIA. Some of the lower grassroots drivers, it is not necessarily compulsory, but actually they've been made so affordable now, most drivers wear them. And to be honest, we always examine them at a time of impact, because you can tell a lot from a helmet and if they're still intact with the hands device, okay? So we always, as soon as the driver, if the driver gets out, we'll ask to look at it. If the driver doesn't get out, when we remove it, someone will be having a very close look at it. The other thing in the corner, you may think is just a glove, but it's not just a glove, okay? So it's called the BioGlove, and what this glove does is record the telemetry from a driver's hand to your oxygen saturations, your heart rate, your movement. And this telemetry is then, from a 3mm chip, goes directly to the Chief Medical Officer's car on a computer screen, and we have that data in front of us. That is really handy for a number of reasons. We can see what is going on with the driver before we actually get to an incident. So as a track doctor or as an extrication doctor or chief medical officer, I would be sat with all that information in front of me. If there was a large impact, I would know if the driver was moving and also what their vital signs were. When we take drivers out of cars, we either take them out rapidly or we take them out controlled, so that we control their C-spine. And if I was concerned about their observations from the gloves on the hand, that would make the difference and me calling them out. Obviously, it's also what you see when you get there, but that is a really good indicator. And the other thing, this medicine is pre-hospital medicine. It's very interesting because we see virtually within seconds of that impact. So concussion is a big thing in the world at the moment, especially in the world of sports. And if a driver isn't moving only momentarily, that is really useful to know, because actually he probably is going to have some element of concussion or head injury, okay? Whereas if we get there after 20, 30 seconds and he's moving sporadically and a bit muddled, we may not know that he had that loss of consciousness. So it's very important for us. And that's been developed in conjunction with Dr. Ian Roberts with the FIA, I do believe. So he is the person to ask about that. Now, one thing I will say about the innovation, which is where engineers also come along, is a lot of what motorsport has done is reactive. So something happens, we think, oh, we don't want that to happen again. Can we solve it? Is there a way of doing it? Whereas actually we'd quite like it to be preemptive. So we think that might happen. Can we solve it in advance? And that's where hopefully we can all work together and make changes rather than an incident occurring like with the hands device and then introducing change. Okay, so I hope we have interested you on our topic today. I would like to say thank you. I think Cristiana is there.
Yeah, very interesting talk, and that's the power of sport. I think developing things fast, and how Claire was saying, we're very reactive. We develop to trying to solve a big problem that we have seen rather than preventive. But I think we'll get there eventually to be preventive one day.
And that's myself and Cristiana trying to look cool outside of the racetrack.
Thank you very much. You do look cool, actually. Thank you very much for such an amazing talk. We have some questions for you. So Banu is asking to Cristiana, what other motorsports methods can we transfer to the medical sector, such as CFD?
So I would say all the simulation that we're doing is transferable to the motorsport sector. And one example is what I did with what I explained with the accident data. Like we collected the data from the car to trying to replicate the accident, but also we collected through the bio gloves, and through the ear accelerometer, the information from the driver and what the driver deceleration of the head is, and what the parameters of his heart and breathing are. So obviously that's are transferable to the medical sector. But I think there is also, it's not just the method that we can transfer, it's also the expertise. So motorsport has got expertise not just in technology, but in materials, in other, like in material, in sensor, in the way to acquire data, and the way to replicate things, like simulate, like, yeah, like it's simulation, but it's empirical simulation, so testing. So things like that can be well placed in the medical industry. For example, with the Oxford box, we are talking with the Manchester University, with the aerosol scientists at the moment, and they have got a way to empirical testing and replicate the aerosol box, but they want us to go there and see what can be improved, or because it takes so long to do it, while normally in motorsport everything is very quickly. So I think is this a fast turnaround that we are used to can somehow be used as well to implement things that you are already have got in the medical sector, and they may just need a small tweak to be faster and to be usable in a different way.
Okay, thank you. So Banu also had a comment for you. As a CFD scientist, it's great to see what can be done with the same method. Transferring the methods used in motorsports and aerospace to the medical field is just perfect. Thanks for the great presentation. It was a very nice indicator of how to solve the current problem, COVID-19, with the Oxford box. Thank you very much, Cristiana.
Thanks.
Then we have some. Yeah. Sorry.
No, thanks a lot for inviting us. It's like it was very great to be there here, and also to hear Pari, that the talk was fantastic.
Thank you very much. We have some questions as well for Claire. So your interest in male-dominant field is very noticeable for audience. How do you encourage more women to for the motorsport?
So I would say always just ask. I honestly, I watched it as a child growing up, didn't have anyone in the industry. And I've learned if you actually approach people and ask them or email them, they will actually be very supportive of you and encouraging you to do it. And I think it's there if you will persist for the opportunity. I think what Cristiana said about having family and traveling and things like that is hard. I do apologize if you saw my son earlier run in. That was a great demonstration. But I do think it is a juggle, but you can specifically do it as a woman. But I do think sometimes you end up maybe as a female, and I think this is true in a lot of professions, you feel you have to be that much better than the boys, because that's just to try and get noticed, because you want to be there by merit. So sometimes you often put pressure on yourself, which isn't necessarily there from others, I would say.
Thank you very much. So following this question,
can I just add one thing? Is like so Claire, myself, and the other ambassador for Girls on Track UK and Dare to Be Different, we trying to encourage a lot of girls into the profession as either engineer or in motorsport, and we actually have done quite a nice podcast on that. It's called Silverstone Inside, that if anybody wants to have a look, that with another two great women in motorsport as well, trying to demystify the idea of being a woman in motorsport and tell lots of nice and funny story and how we got there and how someone should do. And I think is, as Claire said, it's all about trying and asking, and if there is any difficulties, ask for help. It's a great community, the one of women in motorsport. So, and we are all here to help.
Okay, thank you very much. We will for sure check your podcast. So following this question, actually, I had a question of how do you balance the personal life, the children, your family, and the overwhelming workload that we can see that you have?
Is that to me?
For both of you.
For both of us, right. Cristiana, you can go first with that one.
Well, first of all, I've got an amazing husband. I have to say that. It's like it's always price the husband in this case. But it's like, yeah, he's out actually with the kids to give a bit of space. But yeah, he works in motorsport as well, and we really share the loads in everything. And we always have been working like a team where I've got 3 boys, so it's kind of like everything is possible, and family is not a stop on what you want to do. I think you just have to find the right person that you can share the passion and you can share the family as well. And as well, there is we quite a fortunate community as well. I had meetings sometimes where I take one of my son and nobody has ever said anything. Or if I have to meet at the racetrack, I normally take a couple of them, and there is always like a racing driver or a mechanic that can look after them for half an hour. So in that way, it's hard, but I think if you think out of the box and if you think that we all have the same problem, then you are there and you can ask for help. It's not a problem asking for help, and that is the main thing that I say is like, yes, we all face the same problem with childcare, with trying to prioritize things, and sometimes you can't give priority to everything. But at the same time, because we all face the same problem, it's not a problem. It's as well accepted. I think is at the beginning. I think the first time I took one of my kids at the racetrack was about 10 years ago for a meeting, and someone looked at me really not very nicely, just put in this way, and I just give an ice cream and some coloring pen to my son, and it was fine. So I think it's all about trying to demystify these things where you have to be in a meeting, you have to be nicely dressed, there must be no kids and no other people. And I think COVID has done a lot for that, because we are all working remotely now, and we are used to kids coming in, and to the fact that maybe you start a bit late because the internet is a disaster. And so in that respect, I think hopefully society will advance a bit faster if you want. But yes, you can have a job in motorsport and you can be a mom as well. I don't think is a limit, and there is no limit if you really want to do something. That is my feeling, at least.
And I like saying with Cristiana on the back of that, I mean, I have a very good support network in place. My husband, he's actually medical as well. But we've even to the point that we split maternity leave and things like that, so we could both focus on careers. And he knew I was passionate about this when he met me, and so he's been very supportive, and my mum and the rest of my family have been. And in fact, I can hear the children in the background now. So they've been very supportive. But also, I think it's important to get that balance. I admit that sometimes I can feel a bit imbalanced with work and everything else going around, but actually you can find a balance, and it's about using your time wisely as well, which I think I can sometimes be a good procrastinator, I'll be honest. And it's about not getting distracted and actually going on the internet to do what I'm meant to be doing instead of reading something entirely different.
Okay, thank you for these tips. And yeah, we all can be some kind of procrastinators sometimes. So we have a final question from Banu. With engineering methods, it is possible to evaluate situations under different designs different materials, or different physical conditions. For this, the most ergonomic helmet, seat, or many vehicles can be redesigned. It should be awesome to evaluate in this area from a medical perspective and from a driver's eye. It must be great to perform in person and to have information about their biomechanical effects and results. Do you have more innovative ergonomic design ideas? You are there to be different ambassadors as well. So can you tell us what kind of community it is and how can we be part of it as well?
So for the first question about the new device, there are some new devices actually that are being studying at the moment from the FIA safety department. So what was the FIA institute that which I was part in 2016 actually became the FIA safety department, and there are always new devices in there. Like 2 years ago, when I did my last study for them, we were actually studying concussion for rally cars, and we were instrumenting the seat and the helmet and everything. So I'm sure that something else will come out from that. And they have got some fantastic engineers as well that are working on new devices. We got 2 years, I think 2 years ago, we have introduced as well something for checking the tensioning of the seat belt to make sure that the driver do their seat belt okay. So there are other devices coming up. It's just a matter of time and the introduction, and as well of cost, because some devices are really expensive, so they can only be introduced like in Formula 1 or in the upper series like Formula E. But what as well the FIA, that is our federation, trying to do is trying to investigate in how to make the device cheaper, so the whole motorsport world can benefit from that. And I think that affordability of the device is quite important as well at the moment, especially with the fact that motorsport has not been on for 3 months, and is a very different season now. So it's quite a big point. It started to be a big point 4 years ago, but I think now is coming on quite a lot. But yeah, and another device that's coming up for kind of refreshing is the camera that is on the mirror of the F1 cars, and that camera is actually able to capture 200 frames per second. And that is to being able to actually link the data that we get from the ear plug accelerometer with the image of the head moving. So there are things that are progressing and that have been introducing and that are actually refreshing every couple of years because the technology moves on.
And I think going on to that, it is quite interesting Cristiana mentioned cost, because I think I said the hands devices initially were very expensive and they've come down a lot, which means the uptake is so much better in the grassroots racing. And I think that's something really important, because a lot of these innovations actually then come through motorsport and then come into everyday life as well, because we see the improvement in safety that then can be replicated in road cars, which I think is fascinating as well. Your second question though, Dare to be Different, or Girls on Track UK as it is now. So there is a Facebook community. There is also the website. If you go to, it's Dare to be Different, the website, it may have been updated to Girls on Track.
I think it will be under the Motorsport UK website. So if you go to Motorsport UK website, there will be a dedicated page for Girls on Track run by Motorsport UK. And the community will be actually passed over through the Motorsport UK. And the people are the same. It's just like, as Claire said, is a change of banner in the sense that Girls on Track is a more of an international program. So each country have got its program, rather than Dare to be Different was just a UK program. So it was a very difficult to implement it outside the UK. Well, yeah, so it's expanding. That's it.
And I think with Girls on Track, you can join the community, and I think if you go onto the FIA website, you'll find something similar, join the community, and then there's events in various different countries. And we've been lucky.
there is a Twitter feed, I think, as well. So yeah, that your best choice is actually to follow our motorsport Twitter, that is the motorsport UK one, and then they will, as they announced yesterday, I think, or the day before, about this change from Dare to be Different to Girls on Track UK, you can then follow the instruction that they will give in the next months how to join the community.
So, and it's exciting because it's undergoing change at the moment, but the work that has gone on so far, I think, we've already seen, I think, people and go on and make a difference with more and more girls coming through.
But we want some more doctors, so more practitioners and doctors. I think that is important. And I think a nice story to close with is the fact that the community is also where the innovation is, in the sense that through Claire and myself, through Claire and through our friendship, through the community of myself and Claire, is like Claire put me in contact with Sam, that was another doctor, that put me in contact with Bianca, that is a practitioner a consultant in Oxford University Hospital, and that's how the Oxford box has come to be. They had a problem. We were motorsport, so we must know how to fix it, and that's how we did. So I think the fact that the power of the community is giving advice and be there for each other, but is also, if you hear of someone that needs something and you know someone in the community can do it, that is where the power lies, like connection and networking also beyond the community.
Thank you very much, Claire and Cristiana. It was actually a great presentation from both of you. And you're right, networking community are now the key of innovation and success, not only for females, but for the world. And let's hope that we will all be connected by these kind of communities, like the Clinician Engineer Hub and the Dare to be Different as well. Maybe we can even work together for you to have more clinicians and for us to have amazing speakers as yourselves. Thank you very much.
Thank you for inviting us.
So, Banu, do you want to say some last words before I give the final presentation?
Yeah, it was a very amazing presentation. So thank you, Claire, and thank you, Christina, because this was a very different topic, and it was very nice for the last day of July Female Clinician Engineer webinar. So thank you very much for this amazing presentation. We had devoted July to learning the stories of successful female engineers and clinicians, and this was the last day of our webinars. So I want to thank everyone who presented, who listened, watched us. It was very nice to have a new group to learn together, because we hope the webinars had a guiding role in discussing what has been done, what can be done with a multidisciplinary perspective, and developing innovative ideas, devices, subjects with relevance to healthcare. So I want to thank the founders of Clinician Engineer Hub, Dr. Neil Sharma at first, and Dr. Ali Yetishan and Dr. Matt Spargold. And Clinician Engineer Hub, indeed a non-profit organization with the goal of bringing together collaborative efforts of clinicians, engineers. So this was the first female engineers webinar sessions for July, but I'm sure that there will be more events related to this field with new audience and new speakers. Thank you for being with us today. And now Liana will present the last words, and she will take a last picture of us. Thank you very much.
Thank you very much. Thank you very much, Banu. So our webinar series were actually a success. We had 7 hours of presentations and Q&A sessions. We had different engineering fields that have been presented by our amazing speakers, that were actually 12 in total between the 4 days. But most of all, females were presented their work, and are not just successful in engineering fields or being clinicians, but also in personal life, motivating the future generations of females. So of course, we have to talk a little bit about our two communities that are involved in this webinar series. We have the Clinician Engineer Hub that aims to bridge the gap between the medicine and engineering and makes to bring together the clinician and biomedical engineering fields to provide talented medical students and clinicians, exposing them to the world of clinical medicine, challenges doctors that face in the diagnosing and treating patients, and how to potentially solve these issues with cutting-edge engineering solutions. And we are actually now developing our website that was already created, but now it's becoming better, just like the Dare to Be Different. So we are all evolving together. And of course, I have to talk about another organization that has been involved that I am also part of, the EIT Health Alumni Network, that is a multidisciplinary community of innovators building the future of healthcare. Our slogan is by alumni for all. Our mission is to support the EIT Health by building an active network of alumni dedicated to activities to improve quality of life, active aging, and healthcare across Europe. And our vision is to become the leading European Association of Health, social and life sciences professionals, entrepreneurs, innovators, and executives. So please check our website and register in our website to become part of this community and to get all the amazing opportunities that we have. So I would like to thank everyone, all the participants, all the speakers, my great co-host that has been with me since the beginning, Banu, and all the other people that have been involved. Dr. Neil, who was actually a great person that just went crazy with me saying, oh, let's do this webinar series in July. And he said just, yes, 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 let's do it. And it all started just with a little talk. Just like Claire said, it's all about asking and talking. So thank you very much. And let's just finish with our last picture. We only have, oh, we lost a person.
I think we've lost Cristiana.
Yeah, unfortunately, probably it's her internet.
Yeah, she's just texted me and said it's her internet.
Yeah, I understand. Okay, let's just make a picture together. Say smile. Done? And thank you very much. And I hope to see you soon in another webinar series.
Thank you very much for having me.
Thank you.